welcome to Lesson 6, Loops. This week we'll be talking about a powerful programming concept, looping. The loop is a new control construct that makes it possible to repeat a block of code a number of times. So far, every statement and every function has been executed exactly once, or if some condition was false, not at all. While this is useful, it doesn't exploit the real power of a computer, which is the ability to execute millions or billions of instructions per second. With what we've learned so far, to get our computer to execute 1 billion statements, we'd have to type 1 billion statements. And we'd be typing for many centuries just to get a program to run for 1 second. Fortunately, we can avoid all those centuries of work by using loops. In fact, we've already been using loops in MATLAB without even knowing it. To carry out the command n equals 1:5, for example, MATLAB uses a loop internally to create the vector 1, 2, 3, 4, 5. And to carry out the command total equals sum of n, it uses a loop to add all those 5 numbers. These are implicit loops because we didn't use any explicit loop control constructs. Let's compute the sum of 1 through 5 without using the built-in sum function. We'll use a loop, but we need to design an algorithm that includes the loop. An algorithm is just the computer science term for a step-by-step procedure that solves a problem. And this figure shows a very simple algorithm that will solve our problem. It uses a variable called total to store the sum as we compute it, and it starts by initializing total to 0. The large light blue box represents the loop. It specifies that the statement add n to total be executed repeatedly as n takes on the values 1 to 5, one by one. So the add n to total statement will be executed 5 times. After the 5th time, the loop ends and the program continues to the next statement after the loop. That statement prints out the value of the variable total, which is the result we wanted. Note the curved line with the arrows on it. It shows that after add n to total is executed, control circles back and does it again, and it shows why this control construct is called a loop. That little circle looks like a loop. Let's look at the execution in detail. Warning, this part is really boring. We start by setting total to 0. This step is called initialization, and it happens outside the loop. Now we enter the loop. Since the loop must repeat n for n equal to each item in the list 1, 2, 3, 4, and 5, the first thing that happens when the loop is entered is that n is set to the first item, 1. Then n is added to the total. Since total is 0, n is 1, total equals 0 plus 1, which equals 1. That completes the first repetition of the loop. A repetition is called an iteration, and now it's time for the second iteration. This time n is set to the second value in the list, which happens to be 2. Again, n is added to total. Now total equals 1 and n equals 2, so total equals 1 plus 2, which equals 3. That completes the second iteration of the loop. Bored yet? Me too. Don't say I didn't warn you, but we need to go through this for at least one loop. Okay, for the third iteration, n is set to 3. Again, n is added to total. Total equals 3, n equals 3, so total equals 6. That completes the third iteration of the loop. For the fourth iteration, n is set to 4. And as in every iteration, n is added to the total. Now total equals 6, n equals 4, so total 6 plus 4 equals 10. And that's the end of the fourth iteration. For the fifth iteration, n is set to 5. Again, n is added to the total. Now total equals 10, n equals 5, so total becomes 15. That's the end of the fifth iteration, and we've hit the end of the list of values for n, so the loop ends. And finally, we get to the statement after the loop, which prints 15, and our algorithm is done. You may say this was a complicated way to add 5 integers, and you're right, sure. typing 1 plus 2 plus 3 plus 4 plus 5 would have been simpler. But suppose we wanted to add the first 5,000 numbers. Using a loop, we can just change the 5 to 5,000 and it'll add them all up in an eye blink. Now we're ready to see how we can implement this algorithm in MATLAB. The most frequently used loop construct in MATLAB is called the for loop, and that's what we need. Let's see how we can use it to add 1 through 5. We start by initializing the variable total to 0, just like we did in our algorithm. Then comes our for loop. It starts with a keyword for, and to the right of that is what looks like an ordinary assignment statement, but it's not. Its left-hand side is a variable called the loop index. In this case, the loop index is n. On its right-hand side is a vector. But here's where the difference from an ordinary assignment statement comes in. The vector will not be assigned to n. Instead, the meaning of this special assignment statement is that the index, n, will take on the elements of the vector one by one. At each iteration of the loop, n will get the next element of the vector, stopping with the last one. And that's exactly what we want here. N will be equal to 1, then 2, then 3, then 4, then 5. At each iteration, n is added to the current value of total. So, just as for our algorithm, total keeps accumulating the sum, becoming equal to 1, then 3, then 6, then 10, and finally 15. Once the last element of the vector is assigned to the loop index and used in the block of code inside the loop ends. And then fprintf prints the value of total, which is 15. Okay, let's see this example inside MATLAB. Here's our summing algorithm inside a function called SumIntUp. But instead of adding the integers from 1 to 5, we add up from 1 to n, where n is the input argument. If we run it like this, we get 15, as we've just seen. The good thing with a function, though, is that it's easy to run our loop with different numbers. Let's try 10. Summing from 1 to 10 gives 55. What about 100? That gives 5,050, and so on. Let's run the function with 5 again. First, let's set a breakpoint right here on the second line. I just click the little dash here, and the red circle shows me that my breakpoint is set. Then we can use the debugger to step through. Okay, let's run it with 5 as the input. The green arrow here means that execution has been suspended right where we put the breakpoint, and that we're ready to execute line 2 here. At this point, we have not executed this line yet, so the variable total has not yet appeared in the workspace. But there's already a capital N there, and it's equal to 5. Remember, that's our input argument, and it gets its value from the function caller down here. And it comes into existence when it's assigned the input value, which in this case is 5, and that happens before line 2 is executed. Let's execute line 2 by clicking the Step button. To get that button to show up, click the Editor tab. That tab contains all the debugging tools. Here's the Step button right here. Before I click it, you may remember from our introduction to the debugger that you can also take one step by clicking the function key F7 on a MacBook or F10 if you're using Windows. Okay, as I click Step, watch in the workspace to see the variable total appear with the value we're assigning to it, which is 0. There. Now we're at the beginning of the for loop. Okay, I'm going to execute the first line of the for loop. Clicking Step executes that line. There. The workspace shows that we now have the variable lowercase n here, and it's been assigned the value 1, which is the first element of the vector 1 colon n here. This is a key concept for the for loop, so it's worth repeating. The loop index is assigned the first element of the vector produced by 1 colon n, not the entire vector, at least on the first iteration. On subsequent iterations, it will receive subsequent elements of the vector. Now we're ready to execute the body of the for loop here, with the loop index set to 1. The body comprises just line 4, and that line adds n to total. The workspace shows their values before we take the step, 0 and 1. Okay, I'll click Step now, and we see that total has changed to 1. Clicking Step again here at the end statement results in MATLAB taking the next element of the original 1 to 5 vector and assigning it to little n. We'll see that happen right now. There. Note that we did not see the green arrow go back up to the for line at the top of the loop. That will never happen again through the entire iteration. That line is actually executed only once at the beginning of the loop. It calculates the vector of values, in this case 1, 2, 3, 4, 5, and it sets the loop index to its first value, which is 1 in this case. Then after the first iteration, the next index is actually set at the bottom of the loop. It's the same as if it were set at the top, but that's why you won't see control jump back to the for line. Anyway, now we're ready to execute the next addition. Total is equal to 1, and n is equal to 2. So after executing this line, total will be equal to 3. And 3 it is. As we continue clicking the button to step through the code, we can watch the workspace to see how n goes through all the values to 5 and how total reaches 15. Well, let's do that. Click. Now n is equal to 3. Click. Total is equal to 6. Click. N is equal to 4. Click. Total is equal to 10. Click. N is equal to 5. Click. Total is equal to 15. And we take one more step, and we're out of the loop. The next step will print the result to the command window. Let's do that. Click. And we see the result show up in the command window down here. Take another step. You see this arrow pointing down means we're about to leave the function. The function ends, the step button disappears, and we're done. Let's look at this example one more time. The expression with the for keyword is called the control statement. This is where the index variable is defined and its subsequent values are specified. And it doesn't need a semicolon at the end. The block of code between the control statement and the end keyword closing the loop is the body of the loop. It's the body that gets executed repeatedly using successive values of the loop index. Here the body is a single statement, but in general there can be any number of statements in the body of a loop. Most of the time, the vector to the right of the equal sign in the control statement will be formed with a colon operator, as it is here, but it doesn't have to be. Here's another example. Instead of a colon operator, here we simply use another variable that already contains a vector. In this case, it's a vector of 5 random numbers. This is perfectly fine. The loop index will be assigned the elements of this vector one by one. The body of this loop is a single if-else statement. It prints out one of 2 messages, depending on whether or not the current value of the loop index, which is one of those 5 random numbers, is greater than 1/2. We ran this program, and this was the result. Note that depending on when and how the pseudo-random number generator was initialized, you may get a different random number set when you try it. And unlike Mythbusters, we do encourage you to try this at home. Consider this slight variation of the previous example. We eliminated the variable named list because you can call the rand function, or any other function for that matter, right in the control statement itself. In fact, any valid expression can go to the right side of that equal sign. The values assigned to the loop index don't have to be integers, they don't have to be regularly spaced, or even assigned in increasing order. In fact, they don't even have to be scalars. The general rule is that the loop index will be assigned the columns of the array generated by the expression on the right of the equal sign. If that array is a vector, then those columns will be scalars. As for the body of the for loop, any control construct can be used, if statements, other loops, and so forth, or just lists of statements. Let's see the second example in the editor. And let's use the debugger again to watch it work. Place a breakpoint right here on line 2 and call the function. Well, we've stopped at line 2. Nothing's really happened yet. There's nothing in the workspace. So let's take a step. Well, we see n's equal to 5 over here. That happened right there on line 2. Now we've gotten a set of numbers into list by calling rand 1, 5, because n was equal to 5. And here's our list of numbers. There. 1, 2, 3, 4, 5 numbers. Let's enter the body of the for loop. X gets the first number. Body of the loop consists of a single if-else statement. Let's see what happens. Let's see ahead of time. X is greater than 0.5, right? So that means the if branch will be executed instead of the else branch. And we're in that branch, and the printf executes and says that it's large. Now we're down at the end statement. When we click on that, x will get the next value, 0.9058. So let's do that. And there we see x has the next value. That's also greater than 0.5, so this statement will execute again. And there we have it. The next step, we'll set x equal to the next element, 0.1270. X is not greater than 0.5, so we'll be in the else branch. And there we are. Now we're in the body of the else branch. We'll carry out this fprintf, which says that this number is small. And we'll keep going in that way. You can see x going progressively through the list. Now it's on the last one. That's also large. So it just so happened that in this position in the pseudo-random sequence, we had 4 large numbers and 1 small one. Another step gets us out of the for loop, and one more gets us out of the function. By the way, before we started, the pseudo-random number sequence was initialized to the state it has when MATLAB starts. So if you call RNG of 0 before you call rand check, like this, then you'll get the same numbers. Otherwise, you'll get a different sequence. An interesting question arises when the loop index is assigned a value explicitly by a statement within the body of the loop. The question is this: what's the value of the index on the next iteration? The answer is that it's the next value in the list of values given in the control statement, up here. Assignments to the loop index inside the body of the loop are temporary. They last only during the iteration in which they take place. There's no effect on the original list of values given on the if line at the top of the loop, or on the next value to be assigned to the loop index for the next iteration. Let's see an example that illustrates this point. A modified SumIntUp function that we've named loop test. Inside the loop, we first display the current value of n, then we add 1 to n, and then we add n to total. Let's run it. And we give it the value 5. So what have we learned? The function printed the originally intended values for n as given by 1 to n here, the 1:5 expression. We changed the first value of n from 1 to 2, but at the next iteration we got the originally intended next value from here, which was 2. As we said, changing the value of the loop index is temporary. It applies only to the current iteration. There was an effect of adding 1 each time, though. You can see it in the total down here, which is 20. We added an extra 1 to n each time through the loop, so the total should be 5 more than the sum of the first 5 integers, which is 15, and we did get 20. This rule is ironclad. At the beginning of the nth iteration for every for loop, the loop's control statement will assign the loop index the nth term in its list of values, regardless of any value that may have been assigned to the loop index within the body of the loop during the previous iteration. Finally, a word of caution. Don't change it. Don't change the loop index inside the loop if at all possible. It'll just cause confusion when you read your code later or when someone else reads it. There's very rarely a need to do so, and even then you'll be better off using an additional variable than messing with the loop index. Let's talk a little bit about handling vectors with loops. Let's look at this example. Here MATLAB handled the subtraction of the element 5 from the element 5 and got 0. It handled the subtraction of the element 4 minus 5, got minus 1. 8 minus 7 gave 1, 8 minus 8. It handled every one of these subtractions, element by element. Well, it did that with a loop. The loop's behind the scenes. We didn't write the loop, so we call it an implicit loop. MATLAB does that a lot of times, but we can do it too, out here, in front of the scenes. Let's do it. As soon as I hit return, the work is done, and the results are the same. The for loop does exactly the same thing that the array subtraction operation did. We visit every element using the for loop index, which indexes into U and indexes into V and indexes into W. We get the same result. We had to use the length function here to find out how far to carry the loop. In this case, there's really no reason at all to use an explicit loop instead of the implicit loop. Implicit looping runs faster in general, it's easier to program in general, and it attracts fewer bugs in general. You should use it wherever you can. But explicit looping is much more versatile than implicit looping. In addition to being able to do everything that array and matrix operations can do, for loops in general, can do many things that array and matrix operations can't do. Since we often need to do these additional things, MATLAB includes explicit loops as part of its language. As an example where we must use an explicit loop instead of an implicit one, consider the Fibonacci series. It's defined as a series where the first 2 elements are 1 and all successive elements are the sum of the previous 2 elements. We've got a function here that creates the first n elements of a Fibonacci series called Fibo. Let's see how it works. First of all, we do some error checking to make sure that the user has passed in a scalar, a number that's greater than or equal to 1, and a number that's an integer. In other words, a positive integer. We've done that before. Then down here we set the first element to 1 and the second element to 1. You'll remember the definition of Fibonacci series is the first two elements are equal to 1 and the successive elements are each equal to the sum of the two previous elements. Well, now we enter a for loop that goes from 3 to n. N is the input. Why 3? Well, we've already done 1 and 2. And as you can see on the left side of this assignment statement, we're doing F3 and then F4 and then F5 and so on. On the right side, let's say we're at 3. 3 minus 2 is 1. 3 minus 1 is 2. So this is element F1. This is element F2. So F1 plus F2 gives F3. Let's do one more. Double I, the index, becomes 4. So f of 4 is equal to f of 4 minus 2, that's 2. And f of 4 minus 1, that's 3. So f of 4 is equal to f of 2 plus f of 3. And so it goes. Here we had to use an explicit loop since there's no built-in operator or function that could have done what we needed, summing up the preceding elements of the vector to compute the current one. So the Fibonacci series serves as a simple example of why we need explicit looping. The body of a loop can contain any valid MATLAB statements. That means that a loop can contain another loop. In other words, we can nest for loops. That's in fact what we need to do if we want to perform an operation on every element of a matrix instead of a vector. Let's do this. There we've got some random numbers in A, all integers. And let's do this. Of course, you know what's happened here. We've used the array multiplication operation, so every element in A has been multiplied by the corresponding element in A. MATLAB did this with implicit looping. Just as with vectors, however, we can write equivalent code to do the same thing with loops. I've got an example right here in a file called mul.m. Let's see it. There. This is a script, by the way. You'll remember us talking about scripts at the end of lesson 3. A script is a file that contains just a list of commands instead of a function. You can run it by giving its name as a command in the command window. You can also run it by clicking this Run button up here with the great big green arrow. Let's click the arrow. There it shows that mul is carried out in the command window as if we'd typed it in there ourselves. Well, let's see what value it gave to p. Good, same as the array operation did with its implicit looping. We didn't make an error in our script up here, that's good. Well, let's look at the commands in this script. First, we use the size function up here to find out the dimensions of A, and we put those dimensions in row and col. So row has the number of rows in A, col has the number of columns. Then we enter a for loop here, whose index R, which suggests row, goes from 1 to row. So it scans through all the rows of A. Well, you can have, as we mentioned, any MATLAB command in the body of the for loop, and so we have a for loop in the body of this for loop. This inner for loop is said to be nested in the outer for loop. This for loop's index C, which suggests columns, scans all the legitimate column indices in A. The actual calculation is done in the body of this inner loop, and that body consists of just this one statement. It's a multiplication. It multiplies element RC of A by element RC of A. When we exit this for loop, we've done all the columns for a given row. We repeat by changing the row index by 1, then carrying out this loop again for all the columns of that new row index. And we repeat again for a new value of R. And we carry out this inner loop for all these values of C for that given value of R, and so on. When we exit the outer loop, we're done with the script. Note that we've carried out the outer loop row times, and for each one of those, we've carried out the inner loop call times. So this body here, this single statement, was executed a number of times that's equal to row times call. And that's the same number of elements that there are in the matrix A. So that's all there is to it. Or I should say, there's a lot to it. I say that because this script is a lot more complicated than A dot star A. If we want to follow the order in which the elements are multiplied, we can insert a line right after the multiplication, like this, that prints things out. It'll print the row and the column in parentheses using the %D format with a space between them, and then it'll skip to a new line. Let's try it. And I'm going to need more room than this. I think I'll sacrifice my workspace. So I'll close that and then move the command window over here beside the editor window. There. So let's try it again. This time I'll type mul in the command window. There, you can clearly follow what happened. Remember, the first element is the row. So we did row 1, column 1, row 1, column 2, 1, 3, 1, 4. We're done with row 1. Now we move to row 2 and do columns 1, 2, 3, 4. Then we move to row 3 and do columns 1, 2, 3, 4. When we're doing these columns, we're staying inside this inner for loop. When we're done with the inner loop, we go to a new row in the outer loop and then repeat the inner loop. And we do that over and over and over. While we're at it, we could also insert another fprintf statement right here, like this. It'll print working on row, space, and then it'll print the row number R using the %D format, dot, 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 go to a new line, and then print all this stuff out. Let's try that. There, working on row 1. Well, 1, 1, 1, 1, that's row 1, 2, 2, 2, 2, 3, 3, 3, 3, and so on. This makes it nice and clear. This is called row major order. It means that you visit every element of the first row, then every element of the second row, etc. You can't do this sort of thing to look inside an implicit loop that MATLAB provides, but as a matter of fact, for implicit looping, MATLAB uses column major order. Let's consider another example for nested for loops. I've got an example right over here in a file called asterisks. There it is. Let's run it and see what we get. Well, what we get is a pretty little half of a tree depicted in asterisks. In the first line, see that we get 1 asterisk, the next line 2, then 3, then 4, then so on, until we get to 7 asterisks on the last line. Well, over here in the code, there's nested for loops here. And in the inside loop, we see that it prints 1 asterisk each time through the loop. Its index goes from 1 to mm, and as mm gets bigger, it prints longer and longer lines of asterisks. You can see the outer loop changes mm from 1 to n, which happens to be set equal to 7, which is why we get 7 lines with 7 asterisks on the last line. And you'll notice that after each of the inner loops is finished, this fprintf takes us back to the beginning of the next line. The trick here was that we used the value of the outer loop index to control the behavior of the inner nested loop, which gave us these longer and longer rows of asterisks. This again is something that we could not do with implicit loops.